my lab is a neuroengineering lab, but we really came from neuroengineering and nanoengineering. So I think a lot about how to make very small devices and about how things change as we this length scale, as you go from large devices to smaller devices to the smallest devices. In particular, we've been thinking about how to make and improve brain-machine interfaces. And I think Eddie gave you a fantastic example of the potential of a brain-machine interface, in that case, to actually be able to decode speech. And when I think about the brain-machine interface, it generally consists of three different parts. It consists of obtaining a neural signal, decoding that with some kind of decoder algorithm, and then applying that either for cursor motion or speech on your phone or motion of a prosthetic limb. And what we saw from Eddie really showed the power of current decoding algorithms and the ability to take data and actually interpret it in remarkably facile and specific ways. But it's still a pretty invasive procedure. Those are big electrodes that go in there, and they coat a very large part of the brain. And so one of the biggest challenges for us is looking at how to get this neural signal consistently without doing very much damage. And if we look at what is really necessary, we want to be able to have stable probes that give us consistent signals over time. We want to have them non-damaging, that don't hurt the brain tissue when it goes in. We want relatively high channel count, because the higher the complexity of the task, the more channels you need to actually interpret it. And speech is a great example. And you also want it relatively unobtrusive. If we're going to have people actually using these, we don't want something sticking out of your head going around, right? So all these are critical requirements for brain-machine interfaces. And if we look at the devices that are out there today, you can actually see a number of the past devices here on the first couple panels. These are the only preclinically approved brain-machine interfaces for humans. And so there are these ECOG arrays on the far left, which tile on the surface of the brain. Unfortunately, only limited information exists on the surface of the brain. A lot of the good information is deeper. And so we have to get into that tissue. And one example is here, the Utah arrays. So these look like medieval torture devices. And yet, those little spikes can give you pretty good data. The problem is they do a lot of damage when you put them in, and over time, they no longer work. There are more examples on the right showing more recent things that engineers have been developing. So very small probes on a silicon shank that can insert into the brain and record at relatively high fidelity and density for neural recordings. Now, one of the first questions we asked when we got into this field is, well, how big should these devices be if we're going to avoid damage to the brain when we put them in? And for example, on panel E here, this is a NeuroPixel, which is the latest and greatest silicon probe that was developed. And I asked the developer a couple weeks ago, well, how did you determine what size those should be? Well, he said, 70, 80 microns, that sounds like a pretty good size. It's small. And in fact, it's typically said that, hey, that's smaller than a human hair. A human hair is 100 microns. Well, as far as I know, there's no principle that said that human hair should be able to insert into the brain without damage. And so we asked, what happens as you go to different length scales? So we did the first systematic study of different size probes as they insert into the brain. So here's an example of an 80 micron electrode going into the brain, visualized with epifluorescence. And you can see it compressing the blood vessels and pulling them until they finally tear and rupture. So all the black coming out is blood rupturing as it's going through. And you're going to see it break some of the other vasculature as well as it goes in deeper and deeper until we can't see it anymore. So these small, non-perturbative probes are in fact doing considerable damage as they go into the brain. So we said, well, what happens then as we scale to smaller devices? So we start at 120, and we look at the amount of bleeding observed in a binary sense. Do we see bleeding or not? 120, 100% of the time we see bleeding. At 100 microns, 100% of the time, it always bleeds. 80 microns, we always see bleeding. As you saw, it tears the vessels as it goes in. But all of a sudden, when we go to 50 microns, there's a dramatic drop. Only about half the time do you see bleeding. The other half, we don't see bleeding when you insert. And these are high numbers of repetitions, hundreds of repetitions to get this data. We go a little bit smaller, 20 microns, once in a while. And remarkably, sub 20 microns, you never see bleeding, ever. You can insert again and then again and again, and you don't see bleeding. Remarkable. We were super excited about this, so we called our collaborator, a friend over in the UK who has a very good 2-photon microscope, and we said, hey, can this be right? Do an insertion with a 25 micron wire and see what happens. So here it is. They dyed the probe so you can see it going into the microvasculature where there are 10 micron blood vessels, and you can see it going through and just displacing the blood vessels. They're not rupturing them. And so what happens at this size scale is that it's not a rupture event like with a larger probe, but in fact, right near the edge of the probe is a displacement zone where it pushes the blood vessels aside rather than catches them and causes them to rupture. So if you go small enough, then the entire probe becomes displacement rather than rupture. And indeed, this is what we see at that smallest length scale. You always displace and push away blood vessels rather than catch them and rupture them. So that's a remarkable observation just from a very simple systematic study of what happens as a function of size. So how do we use this then, knowing then that we can make very small probes that are non-damaging? Well, then we make probes that are that length scale and smaller. So these are what we call neuroroots because they're the same kind of size scale as natural human axons in the brain, about sub 10 micron. And you can scale these up and actually implant them into the brain with very low damage. You can also apply this to the peripheral nerve system as well. So here's an image of them going into the peripheral nerve, in the ulnar nerve in this case, where they actually distribute through the nerve without harming it. We also can make parallel arrays of very small wires, and this is what Matt Engel presented yesterday that's now spun off and launched out of the lab for the company Paradromics. Okay, so that's one of the big problems, is damage. But there's another big problem, which is scaling. And so if I look at how we currently scale how many devices that we have, here's one fantastic example from UCSF. It's a beautiful piece of work, but you can see some of the challenges in the field in it. So this is a 16 electrode probe at the end of a silicon shank. And then if I want more of them, I will make 4 probes on that. And then what if I want more than 4 times 16? Well, then I stack them up. And I get this big stack of devices, and that looks something like that. And so this is very powerful, gets you about 1,000 electrodes, but this is not going to scale for humans. You don't want to have that big block sitting on your head. So we need some way to break this scaling paradigm of just connectorizing them to these big, fat connectors. And if you know much about neuroscience in terms of the hardware, the whole bane is really about connectors. That if I have these tiny little neuroroots, those go to, in this case, 32 different pads, and from there, I have to go to a computer through a connector. So there's always this big chunk of plastic in between your electrodes and your computer. That's a big problem, and we don't have a solution for it yet. But we've got to get rid of those connectors if we're going to make something that is going to be really powerful and small. And yet, if I think about this, we have devices all around us that have millions of independent little pixels, each one that can record and stimulate voltage. And so in our mind, the question became, how do we connect these two? Why go to a normal CMOS chip? We can go onto the surface of a pixel array, like a camera or a display chip. All right? It's not entirely obvious how you do this, but we actually were inspired to do something like a Post-it note. What if it was just as simple as placing a Post-it note on top of this chip? And we were inspired in this case by how geckos work. Now this is an interesting example. Geckos have tiny little hairy pads at the end of their fingers. And those tiny little hairs interact through van der Waals forces, a very weak force that allow them to climb all over the walls in your hotel room in Hawaii. Okay? And it's really a matter of scale. That at that small scale, those weak forces are very, very powerful. That inertia and mass that we have at our macroscopic level don't really apply here. And so we took that principle and said, can we make something different that would use it to make good contacts? So this is what we call a Gecko pad. It's got an insulator on the polymer on the top. It's got a pixel down below, and it's got this metallic pad that's suspended over the metal pad. And all we're going to do is take this and just plop it down on top of our pixel surface. And in fact, when you simulate, what happens is those weak forces will snap that small pad into contact with a pixel, just because they're very, very small, 10 microns or so. And so you can get automatic connection without having to do anything other than place one on top of the other. And so this has allowed us then to make series of these devices. And here's an example of a few. And then we zoom out. This is what it looks like when you're putting it down. So you can see on the top surface, we've got hundreds of them in contact. And then kind of midway through, we see where they're out of contact. They're kind of coming up and about to become in contact as we roll it down. And this is what one of these looks like on a display chip. Each one of those little pixels is 6 microns, and we can integrate them. And you might say, how do you get a one-to-one contact with each of those pixels? And the answer is, I don't need to. We've got 1 million pixels there, and we've got a few 10,000s of connectors. We don't even worry about that. We can connect all of our electrodes up to the pixels that we need. And in fact, if you're wondering, you can get very good electrical contact just by this snapping method. Okay, so using these two things, knowing that you go very small and knowing that we can connectorize them without any connectors and big chunks of plastic, we can start making what we think is going to be a very non-damaging scaling BMI. Something like this, where we're going to have tiny electrodes coming off the surface, going to a chip, and then eventually going to a wireless antenna on the outside. Each of these then is only a few millimeters in size. And this can be implanted at multiple locations to give you high density, deep data from inside the brain. So, is this the future of BNI? Well, we're yet to find out, but I think what I've hopefully convinced you is a lot of the traditional barriers that have been there in terms of the devices are starting to come down. We can make things that don't damage, and we can scale it up. Thank you very much.